In the vast, sprawling expanse of the universe, our own galaxy, the Milky Way, is just one of hundreds of billions, and at the heart of nearly every one of these immense cities of stars, there lurks a monster. These are not monsters of myth or legend, but objects of pure physics, so dense and so powerful that they warp the very fabric of space and time around them. We call them supermassive black holes. They are the gravitational anchors of their galaxies. Cosmic behemoths with millions or even billions of times the mass of our sun, all compressed into an infinitesimally small point. Everything in the galaxy, including our own solar system, orbits this central giant in a slow cosmic dance that takes hundreds of millions of years to complete one turn. These supermassive black holes are not just passive anchors, they are active and influential participants in the life of a galaxy. They can feed on surrounding gas, dust, and even entire stars that wander too close. As this material is pulled in, it forms a swirling superheated disk called an accretion disk. This disk can shine brighter than all the billions of stars in the galaxy combined, creating what astronomers call an active galactic nucleus, or AGN. The energy and radiation pouring out from this process can regulate star formation across the galaxy, sometimes igniting it and other times shutting it down. Understanding these giants is therefore crucial to understanding how galaxies themselves are born, how they grow, and how they evolve over cosmic time. For a very long time we believed that these supermassive black holes were permanent residents of their galactic homes. They were born with the galaxy, grew with the galaxy, and would remain tethered to its center for all of eternity. The gravitational pull was thought to be simply too immense for them to ever escape. They were the ultimate prisoners of their own gravity, bound forever to the stellar systems they helped to shape. This picture made sense. It was neat. It was tidy, and it fit with our observations of the countless galaxies we could see, each appearing to have its own central black hole, sitting right where it was supposed to be. But the universe is often more complex and more violent than our neat theories initially suggest. What happens when galaxies, these great islands of stars and gas, collide? These cosmic smash-ups are common events in the life of the universe. Our own Milky Way is on a collision course with the neighboring Andromeda galaxy, set to merge in about 4.5 billion years. These mergers are chaotic, transformative events that scramble stars and trigger furious bursts of new star birth. And if galaxies can merge, then it stands to reason that their central supermassive black holes can merge as well, leading to an even more dramatic and powerful cosmic event with unforeseen consequences. The idea that a supermassive black hole could be forcibly ejected from its home galaxy is not a new one. In fact, it is a theoretical prediction that has been around for about half a century. Physicists and astronomers, running complex calculations and computer simulations, began to wonder what would happen during the most extreme events in the universe, such as the merger of two galaxies. They realized that the immense forces involved could potentially be enough to overcome the gravitational anchor of a black hole and send it hurtling into the void of intergalactic space. This was a startling idea, suggesting that there could be lonely, wandering black holes, stripped of their galaxies, roaming the dark spaces between the great cosmic cities. One of the primary mechanisms they proposed for this ejection is something called gravitational wave recoil. When two black holes spiral into each other and merge, they release an enormous amount of energy in the form of gravitational waves, ripples in the fabric of space-time itself. If the merger is not perfectly symmetrical, for instance, if the two black holes have different masses or are spinning at different rates, then these gravitational waves will be emitted more strongly in one direction than another. Just like a rocket is propelled forward by shooting exhaust backward, the newly merged black hole can receive a powerful kick in the opposite direction. This kick can be so strong that it sends the black hole flying out of its galaxy at millions of miles per hour. Another way to unmoor a supermassive black hole involves a complex gravitational dance with three bodies. Imagine a scenario where two galaxies have already merged, and their central supermassive black holes have formed a binary pair, orbiting each other. Then, a third galaxy merges with this newly formed larger galaxy, introducing its own supermassive black hole into the central region. This creates a chaotic three-body problem. In this gravitational tussle, it is possible for two of the black holes to form a closer pair, and transfer their orbital energy to the third one, flinging it away with tremendous speed, much like a slingshot. It is a game of cosmic billiards played with the most massive objects in the universe. For 50 long years, this idea remained purely in the realm of theory. It was a fascinating and dramatic possibility, but there was no direct observational evidence to support it. Astronomers knew what to look for, in principle. A runaway black hole wouldn't be completely invisible. As it plowed through the thin gas that exists between galaxies, it should create a shockwave, and its immense gravity should pull in some of that gas, potentially triggering a trail of new star formation behind it. But space is vast, and such an object would be incredibly faint and difficult to spot. It would take a new generation of telescopes, with unprecedented sensitivity and power, to turn this 50-year-old prediction into an observed reality. Our story now takes us to a distant corner of the universe, to a place 8.8 billion light-years from Earth. Here, astronomers using the powerful gaze of our space telescopes found an object of peculiar beauty and scientific interest. It is a system of merging galaxies, a chaotic and energetic place where two great stellar cities are in the process of colliding and combining into one. Because of its striking appearance in astronomical images, which resembles the face of a wise bird, it was affectionately nicknamed the Cosmic Owl. The two brightest points of light, the glowing hearts of the original galaxies, form the owl's large, luminous eyes, while a bridge of gas and dust connecting them creates the impression of a sharp beak. The eyes of the cosmic owl are what we call active galactic nuclei. This means that the supermassive black holes at the centers of these two merging galaxies are actively feeding on the vast amounts of gas and dust being funneled towards them by the collision. This process makes them shine with an incredible intensity, visible even from a distance of nearly 9 billion light-years. The beak is a region of intense star formation, a stellar nursery where the compression of gas from the galactic merger has triggered the birth of millions of new, hot, blue stars. This system is a perfect laboratory for studying how galaxies evolve through mergers, a process that is fundamental to the structure of the cosmos we see today. It was in this dynamic and turbulent environment that astronomers began to notice something unusual. While studying the detailed images of the cosmic owl, they saw a feature that did not seem to belong. Extending away from the central region of the merging galaxies was a long, remarkably straight and narrow line. It was a faint streak, almost lost in the background noise of deep space, but it was undeniably there. This was not the typical tidal tale of stars and gas that gets flung out during a messy galaxy merger. Those are usually broad, curved, and diffuse. This feature was different. It was sharp, linear, and pointed away from the galactic chaos like an arrow. This mysterious streak immediately caught the attention of the research team, led by Peter Van Dockum of Yale University. What could create such a peculiar straight-line feature in the aftermath of a galactic collision? It was a puzzle that demanded a closer look. The feature was incredibly long, stretching for an astonishing 200,000 light-years, which is twice the diameter of our entire Milky Way galaxy. It was a cosmic thread of unimaginable scale, and its origin was a complete mystery. It was this faint, straight line, discovered by chance in the cosmic owl system, that would ultimately lead astronomers to the solution of a 50-year-old cosmic riddle. The first hint of this extraordinary phenomenon came not from the newest telescope, but from a seasoned veteran of space observation, the Hubble Space Telescope. For decades, Hubble has been our premier eye on the cosmos, delivering breathtaking images that have revolutionized our understanding of the universe. While examining the cosmic owl galaxy system, Hubble's sensitive cameras captured the faint straight line that seemed to emanate from the galactic merger. This linear feature was so unusual that it immediately stood out from the chaotic swirls and arcs of stars and gas that are typically associated with two galaxies colliding. It was a cosmic anomaly, a straight edge in a universe that prefers curves. The team of astronomers was perplexed. This streak, stretching across an immense distance, looked like a wake, the kind of trail a boat leaves as it moves through water. But what could possibly be powerful enough to plow through the thin gas of intergalactic space and leave such a colossal trail in its wake? The length of the streak was staggering. At 200,000 light-years, it suggested that whatever created it had been traveling on this straight path for a very long time, moving at an incredible velocity. It was a clue, pointing to an object of immense mass and speed that had been violently ejected from the heart of the cosmic owl's merger. Hubble's observations showed that this long tail was not just a smear of diffuse gas, it was dotted with bright, blue knots of light. These are the telltale signs of newly formed stars. This suggested that whatever was leading this charge was compressing the sparse gas in its path, triggering it to collapse under its own gravity and ignite into starbirth. The runaway object was acting like a cosmic plow, creating a furrow of new stars as it sped through the intergalactic medium. It was leaving a breadcrumb trail of star formation, a glowing testament to its high-speed journey through the dark emptiness of space. However, while Hubble provided the tantalizing first clue, it couldn't provide the definitive proof. The images were powerful, but they couldn't confirm the nature of the object at the tip of this long streak, nor could they measure the dynamics of the gas to prove it was being compressed. To do that, astronomers needed a new kind of observatory, one that could see the universe in a different light and dissect that light to reveal the motion and composition of the material. They needed to see the invisible. For that, they turned to the most powerful space observatory ever built, the James Webb Space Telescope, to take a closer look at the tip of this mysterious cosmic arrow. With the tantalizing evidence from Hubble in hand, the astronomers pointed the James Webb Space Telescope, or JWST, towards the cosmic owl. The JWST, with its giant golden mirror and its ability to see in the infrared part of the spectrum, is, honestly, perfectly designed to peer through dust and see the faint heat signatures of distant objects. The team focused JWST's instruments on the very tip of the mysterious 200,000 light-year-long streak. They were looking for the so-called boat that was creating this incredible cosmic wake. And what JWST saw provided the smoking gun they had been searching for, confirming that this was indeed the trail of a runaway supermassive black hole. At the head of the long tail of stars, JWST detected a compact, bright source of light. This was the black hole itself, or more accurately, the glowing accretion disk of gas that it had gathered on its journey. But, the most crucial piece of evidence came from what was happening in the space directly in front of this object. The black hole is moving at an incredible speed, estimated to be around 3.5 million miles per hour, or about 1,600 kilometers per second. As it hurtles through the thin, diffuse gas that permeates the space around the cosmic owl, it's actually moving faster than the speed of sound in that medium. This creates a phenomenon known as a bow shock. A bow shock is similar to the shockwave created by a supersonic jet flying through our atmosphere. The black hole is piling up and compressing the intergalactic gas in front of it, heating it to extreme temperatures and causing it to glow brightly. This glowing, compressed region of gas forms a distinct arc-shaped feature right at the front of the runaway object. It's really the cosmic equivalent of the V-shaped wave that forms at the bow of a speedboat as it cuts through the water. The JWST's instruments were sensitive enough to clearly image this faint, glowing arc of superheated gas, providing the first direct visual confirmation of the bow shock. This observation was the definitive piece of the puzzle. The combination of a long, straight wake filled with new stars and a bright, compact object at the tip preceded by a clear bow shock could only be explained by one phenomenon: a supermassive black hole that had been ejected from its host galaxy and was now careening through intergalactic space. The prediction made by theorists 50 years ago was no longer just a theory. Astronomers were now looking at the real thing, an object designated RBH1 for Runaway Black Hole 1. The cosmic owl's secret was out, and it was honestly more spectacular than anyone had imagined. The confirmation of the runaway black hole wasn't just based on a pretty picture of a bow shock. The James Webb Space Telescope has a powerful tool called a spectrograph, which acts like a prism, splitting light into its constituent colors or wavelengths. By analyzing the spectrum of light, astronomers can learn an incredible amount about an object, including its chemical composition, its temperature, and, most importantly, its motion. The team used JWST's NIR spec instrument to carefully dissect the light coming from the gas in the bow shock region, and the results were, in the words of the research team, overwhelming evidence for their conclusion. The spectrograph measured the light from specific elements, such as hydrogen and oxygen, within the gas. It revealed a clear and dramatic velocity gradient across the bow shock. This means that the gas on one side of the shock was moving at a very different speed compared to the gas on the other side. The data showed that the gas in front of the black hole was being rapidly accelerated and compressed, with a velocity difference of about 600 kilometers per second over a very short distance. This is exactly what you would expect to see in a powerful, supersonic shockwave. It was the kinematic signature, the motion-based fingerprint of a bow shock. Furthermore, the light from the 200,000 light-year-long tail told its own compelling story. As the runaway black hole speeds through the intergalactic medium, its immense gravity pulls in and funnels the gas into a narrow wake behind it. This process of collecting and compressing gas is what triggers the formation of the young blue stars that Hubble had first spotted. The wake is not just a passive trail, it is an active stellar nursery, a linear galaxy being created on the fly by the passage of this cosmic wanderer. The properties of these stars, their age and distribution, are consistent with having been formed sequentially as the black hole blazed its trail across space. So, the evidence is threefold and mutually reinforcing. First, there is the morphology, a long, straight tail pointing away from a galactic merger, with a bright object at its tip. Second, there is the star formation, a trail of young blue stars that indicates gas is being compressed in the wake. And third, there is the kinematics, a term for the physics of motion, the spectroscopic proof of a powerful bow shock at the head of the trail, where the black hole is supersonically slamming into the surrounding medium. Together, these pieces of evidence paint an unambiguous and astonishing picture of a supermassive black hole, cast out from its home and roaming the cosmic wilderness. The question that naturally arises from this incredible discovery is, how? How can an object with the mass of millions of suns, the gravitational anchor of an entire galaxy, be thrown out with such violence? As theorists predicted decades ago, the answer lies in the most energetic events the universe has to offer: the merger of galaxies and their central black holes. The cosmic owl system, being a site of a galactic merger, is the perfect crime scene. There are two main scenarios that can lead to such a dramatic ejection, both of which involve a powerful gravitational exchange. The first mechanism is known as the gravitational wave recoil, or the gravitational rocket. This happens when two supermassive black holes, brought together by the merger of their host galaxies, finally spiral into one another and coalesce into a single, larger black hole. According to Einstein's theory of general relativity, this violent merger releases a colossal amount of energy in the form of gravitational waves. If the merger is perfectly symmetrical, if the black holes have equal mass and spin, the waves are emitted equally in all directions. But in the messy reality of the universe, such perfect symmetry is rare. If one black hole is more massive than the other, or if they are spinning in different directions, the gravitational waves will be radiated more powerfully in one direction. To conserve momentum, the newly formed, merged black hole receives a kick in the opposite direction. This is the same principle that propels a rocket. The rocket expels gas downwards, and the rocket moves upwards. In this case, the merging black holes expel space-time ripples in one direction, and the final black hole recoils in the other. If this kick is powerful enough, exceeding the galaxy's escape velocity, the black hole is launched into intergalactic space, becoming a runaway. The second possibility is a dynamic three-body interaction. This scenario unfolds when a third galaxy, with its own supermassive black hole, merges with a galaxy that already contains a binary pair of supermassive black holes from a previous merger. This creates a chaotic gravitational dance between the three massive objects. In this cosmic mosh pit, energy and momentum are exchanged between the three black holes. A likely outcome is that the two most massive black holes will form a tight binary, and in doing so, they will transfer a huge amount of their orbital energy to the third, lightest black hole. This transfer acts like a gravitational slingshot, flinging the third black hole out of the galaxy at an enormous speed. Given the environment of the cosmic owl, either of these violent scenarios is a plausible explanation for the runaway we now see. The confirmation of RBH1, the runaway supermassive black hole in the cosmic owl system, is a monumental achievement in astronomy. It represents the culmination of 50 years of theoretical work and a patient, technologically driven search. For half a century, the idea of rogue black holes wandering the intergalactic void was a compelling but unproven concept, confined to the pages of academic journals and the pixels of computer simulations. Astronomers had calculated that it should be possible, but the universe had stubbornly refused to reveal an example. The discovery is a powerful testament to the predictive power of physics and the relentless ingenuity of scientists and engineers who build the tools to test those predictions. This discovery was not made overnight. It required a symphony of observational power, combining the keen eye of the Hubble Space Telescope, which first spotted the anomalous streak, With the unprecedented infrared sensitivity and spectroscopic capabilities of the James Webb Space Telescope, Hubble gave us the first clue, the where, but it was JWST that provided the definitive what and how. It could measure the motion of the gas and confirm the existence of the bow shock, turning a fascinating candidate into a confirmed discovery. It highlights how progress in astronomy is often driven by new technology that allows us to see the universe in ways that were previously impossible. Finding this object closes a significant chapter in our understanding of galaxy evolution and black hole dynamics. It proves that the centers of galaxies are not static, unchanging places. They are dynamic and at times, incredibly violent. The ejection of a supermassive black hole is a profound event for a galaxy. It loses its gravitational heart, which could have dramatic long-term consequences for the orbits of stars in its central regions and its potential for future growth. The discovery of RBH1 transforms our picture of the cosmos, adding a new population of objects to the cosmic zoo, the galactic orphans, the wandering giants. The significance also lies in the fact that this is likely not a one-of-a-kind object. If the conditions for black hole ejection, galaxy mergers, are common, and we know they are, then there should be many more of these runaways out there. This first discovery is the proof of principle. It tells us that our theories were correct and shows us what these objects actually look like. It provides a template, a set of observational signatures that astronomers can now use to hunt for more. We have found the first needle in the cosmic haystack, and now we know what the needles look like, making the search for others a much more tractable problem. The discovery of the first runaway supermassive black hole is not an ending, but a beginning. It has opened up an entirely new and exciting field of astronomical inquiry, the search for the population of cosmic wanderers. Now that we know what to look for, a long straight trail of young stars, with a bow shock at its tip, astronomers can begin a systematic hunt for more of these objects. Finding just one is a landmark, but finding many will allow us to understand how common this phenomenon is, what types of galaxy mergers are most likely to produce them, and what role these ejected black holes play in the wider cosmic ecosystem. The next generation of space telescopes will be instrumental in this search. Upcoming wide-field survey missions, such as Europe's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, are designed to map vast areas of the sky with incredible depth and detail. Their primary missions involve studying dark energy and exoplanets, but their massive datasets will be a treasure trove for astronomers searching for rare and unusual objects. Algorithms can be designed to scan these millions of new galaxy images, specifically looking for the telltale linear streaks that might indicate the presence of another runaway black hole. The hunt is on, and it will be powered by big data and artificial intelligence. Furthermore, future gravitational wave observatories will provide a completely different way to study these events. A space-based observatory like the Laser Interferometer Space Antenna, or LISA, will be sensitive to the low-frequency gravitational waves produced by the mergers of supermassive black holes. When LISA detects such a merger, it will also be able to measure the kick velocity imparted to the final merged black hole. Astronomers could then use this information to point conventional telescopes, like JWST, to the corresponding galaxy, and search for the telltale wake of the newly ejected object. This combines our two windows on the universe, light and gravity, into one incredibly powerful tool. This first confirmed runaway black hole, RBH1, is a pioneer. It has journeyed 200,000 light-years from its home, and its discovery has journeyed 50 years from a theoretical prediction to an observational reality. It reminds us that the universe is a dynamic, evolving, and often violent place, filled with wonders that continue to challenge and expand our understanding. As we continue to scan the skies, we will undoubtedly find more of these lonely giants, each with its own story of a cataclysmic past. And with each new discovery, we will piece together a more complete and profound picture of the life and death of galaxies and the restless hearts that once lay within them.